Today we're going to explore systems thinking based on Donella Meadows' brilliant book, Thinking in Systems: A Primer. We'll look at a range of simple but powerful systems, each behaving in its own unique way. Meadows calls this collection the Systems Zoo. Now, while we'll talk about each system as if it stands alone, in real life they're usually all tangled together, overlapping and influencing one another. To start, let's break a system down into four main parts: stocks, flows, feedback loops, and delays. A stock is anything you can measure at a point in time. Think of the water in a bathtub. Flows fill or drain that stock. So, in the bathtub example, the tap and the plug hole control the flow. Feedback loops are the reason systems don't just drift aimlessly. A balancing loop tries to maintain a target or return things to normal. A reinforcing loop does the opposite, pushing things to grow or spiral further. And then there are delays, the pause between cause and effect. Even short delays can make a system behave in unexpected ways. Let's begin with a classic, the thermostat. This is a simple one-stock system where the stock is room temperature. There are two balancing loops here. One loop switches the heating on when it gets too cold. The other accounts for heat escaping to the outside world. They push in opposite directions, but together they help keep the temperature steady. This example shows how systems use feedback to keep things stable, adjusting outputs to stay near a set target. Next up, a different kind of one-stock system, car stock at a dealership. Just like the thermostat, this setup has balancing loops. One loop handles supply, new cars being delivered. The other reflects demand, cars being sold. But here's where it gets interesting. This system includes delays. It takes time for staff to notice that stock is running low, decide to place an order, and then wait for the delivery to arrive. Even a small steady rise in demand can trigger oscillations where the stock keeps swinging too high or too low. And here's the twist. Trying to react too quickly or reduce the delay can backfire, causing the system to overreact and make things worse. Now, let's look at a system built around reinforcing feedback oil extraction. The more oil a company sells, the more money it makes. It reinvests that money into better equipment, which boosts production, which then makes even more money. This reinforcing loop creates exponential growth, at least for a while, but then limits appear. In this case, it's the finite oil supply. As the oil stock runs low, a balancing loop kicks in, reducing how much can be extracted. But it's not always so simple. If oil becomes scarce, prices can shoot up, tempting companies to extract even faster. That speeds up the loop, but it also speeds up the collapse. This is a perfect example of how a system that seems to be growing successfully can hit a wall or even destroy itself if we ignore the limits. Each of these examples shows us a pattern that appears again and again in real-life goal-seeking systems like thermostats. Try to reach a stable point. Oscillating systems like car inventories bounce up and down due to delays. Reinforcing systems like oil extraction grow fast until they hit a limit. These patterns aren't just theory, they show up in the economy, nature, society, and even inside organizations. So what's the point of all this? Well, Donella Meadows makes it clear if you understand a system's structure, you can better predict how it behaves. You stop being surprised by outcomes. You start to see problems before they happen. And most importantly, you make better decisions. Systems thinking doesn't give you a magic fix, but it does help you ask better questions. What are the stocks? What are the flows? Where are the delays? Which loops are in charge? Because once you can see the system, you can change how it works.